Now we're ready to talk about the most famous game in game theory, which you maybe have heard of before, and that's the prisoner's dilemma. So it's a two-person, two-action, simultaneous game. So we'll set up our table here. So the two players, here's how the story goes. There's two kind of petty criminals who don't know each other. We'll call them A and B. And they meet at a bar. They decide to do a crime together. They are caught and they're put into separate cells. And the district attorney arrives and she gives them both a deal. She gives them both the same deal. And that is they have the choice to confess or remain silent. So each player is going to have to separately decide whether to confess or be silent. So if they both confess, well then they have, plenty of evidence, and so they're both going to go to jail for 5 years. So I made those payoffs negative. The payoffs are years in jail. And they're negative because a year in jail is a bad thing, right? So 4 years in jail is better than 5 years. So if we make it negative, -4 is bigger than -5. If neither of them confesses, if they're both silent, then there's just circumstantial evidence. She won't really be able to put on as good a case, and they'll both only spend 1 year in jail. Now, if one of them is silent and the other confesses, well then the person who confesses is like the state's witness. So they're helping the prosecution, they're going to get a break, and of course they're going to tell the story in such a way that it was really the other person was the mastermind and they were just in the wrong place at the wrong time and they didn't really do that much. So the person who confesses is going to get away without any jail time, and then the person who was silent, well, they didn't defend themselves, they let the other person tell the story, and so we're going to throw the book at that person and they are going to get 20 years, the maximum penalty. And the same will happen here. Player A is silent and player B confesses. Player A will get 20 years and player B will get nothing. So that is the classic tale of the prisoner's dilemma. And what happens in this game? Well, anytime we're seeing a simultaneous game, we want to use best response analysis. We want to see if we can find Nash equilibrium. What should player A do? Well, player B confesses, and then we're in this left-hand column here. Player A should confess because -5 is better than -20. And if player B is silent, if we're in the right-hand column, then player A should also confess because 0 is better than -1. So player A has a dominant strategy to confess. Confessing is better no matter what player B does. So player A doesn't really need to worry about what player B might or might not do. If player B confesses, player A should confess, and if player B is silent, player A should confess. Confession is really the best move, gets the higher payoff no matter what player B does. And it's a symmetrical game, so the same is true here for player B. In the top row, player A has chosen confess. Player B can choose silent and get -20, or confess and get -5. -5 is better. If player B has chosen silent and we're in the bottom row, player B can choose silent and get -1, or choose confess and get 0. Well, 0 is better than -1. So player B also has a dominant strategy to confess. And we have only one Nash equilibrium in the game, which is both players confessing. That is the only stable outcome. When they both confess, they both made a best response to each other. That's our definition of a Nash equilibrium. All the other combinations are not a Nash equilibrium because one or both of them wants to change their choice. So what makes this an intriguing game and a dilemma is that you can see, maybe you already noticed that both of them would be better off if they were silent. right? The -1 is better for both players, but this one is not in equilibrium, right? The equilibrium outcome is worse than the non-equilibrium outcome. And so those are the two things that we need in a game for it to be a prisoner's dilemma. We need dominant strategies for both players. And we need the dominant strategies to lead to a worse payoff, a worse outcome for both than the dominated strategies. So, yeah, if we have a dominant strategy, the other strategy is dominated. We will sometimes call it that. So that's a prisoner's dilemma, and we'll talk in the next videos about situations in oligopoly and in other kinds of situations where we see this kind of dynamic, where there's dominant strategies for the players, but it's leading to a worse outcome for everyone. Let me know if you have questions.